Okay, so let's now move on to actually developing the theory step by step. The first step being writing down the Navies-Stokes equations in 2 dimensions in full, scaling them, and then seeing how perturbation expansion will arise naturally. So let us begin with the equation of continuity. So we have dou u by dou x plus dou v by dou y equals 0. Now the variables u, x, v and y are dimensionless, so I should include their scale factors here as well. So I'm just going to scale them on the fly, and this is something we have done before. So I urge you to try and scale the problem yourself, pause the video, give it a try, and then you can watch and see whether your ideas are right, and if not, how the calculation actually proceeds. So we have a characteristic scale for u here. We'll just leave it as uc for the moment, and this characteristic scale could come from the motion of the walls, or it could come from the applied pressure gradient, depending on the problem of interest. So I'm going to leave it just as u characteristic for the moment. And then we have the length scale associated with variations in the longitudinal direction. Now this is the key part of the problem, right, where the separation of length scales comes in. So in our problem, let's say that there are some variations, and I know that a typical scale for this is let's say capital L. It could be the length of my entire channel, or it could be the wavelength of waves if it were a very wavy surface, and so on. So let's just take it as L. Right, so I have u by L here. On this side I have v characteristic now, and then the length scale for the y direction, which you could take as some mean height of the surface. Let's just take it as capital H, where in this case H is some sort of mean reference height. So what H is exactly, again, will vary with the problem, right? But we understand the meaning of this term. Okay, so with this now, we can immediately see that these are the only 2 terms in the equation, so they must always be in balance. And therefore, from here, we can say that Vc must be equal to H by L times Uc, which it must be epsilon times Uc, right? Where, of course, epsilon equal to H by L is a small number. Alright, so this choice of scales would then cause these terms to cancel off, giving us just dou u by dou x plus dou v by dou y equals 0. So at all points in the flow, the continuity equation has to hold in its full form. So you can already see that if there is a variations of the flow in the longitudinal direction, there will certainly be a vertical component of velocity to conserve mass. But we can also see that that vertical velocity component is going to be an order smaller than the horizontal component, which is a consequence of the long wave nature of the problem. Right, so the magnitude of the magnitude of the primary component of velocity, the horizontal velocity, is going to be much larger by a factor epsilon, or by a factor 1 over epsilon rather, than the vertical velocity components. So this is the scaling incorporates that physical feature, leaving us with a scale continuity equation which allows for the calculation of v, if only we could obtain u as a function of x. So let's bear that in mind. Let us now move to the momentum equation for the horizontal velocity. So I have here rho sitting on the outside. I have dou u by dou t, and then I have a u characteristic and a time scale, of course, which are yet to be determined, plus u dou u by dou x plus v dou u by dou y equals mu now dou square u by dou x squared plus dou square u by dou y squared. These are my viscous terms. I also have, of course, a pressure gradient, so minus dou p by dou x here, and I have another optional, but since we're considering a general problem, driving force capital G. Now this G could be the applied applied background pressure gradient, right, as we have seen in earlier problems. So if the problem of flat, G would be exactly the pressure gradient throughout the problem. So dP by dx minus dP by dx would be exactly G for flow between flat plates. But since there are some variations, we expect pressure deviations from the linear gradient. So that will all be captured in this P here. And so G can be thought of as a driving pressure gradient, which is constant. And the actual pressure here, the dynamic pressure considers only the variations. Alternatively, G could also represent density times the acceleration due to gravity, the component in the x direction of flow. Right? But in this problem, we will not consider the effects of gravity and only consider the fact that, G could be an applied pressure gradient. And even if you had gravity, it wouldn't really change the basic nature of the problem. Alright, so this G now, let's call it G star because it's as of now, it's a dimensional quantity. Okay, let's introduce scale factors so that these U and X variables can be dimensionless. So this will throw out U characteristic squared upon, now typically I would have L, but I want to take out common H as a length scale. So instead I have L here, but I'm going to multiply and divide by H, which gives me H, and it also gives me an epsilon. Right, so I had UC square by L, I multiplied and divided by H to get an epsilon by H. Here on the other hand, I'm going to have UC times VC, but if I replace by VC by epsilon UC, I get UC square, I get an epsilon factor, and I also get H coming out of Y. Now for my time scale, what I would like to do is retain in general the time variations in the problem and have the same magnitude as the other inertial terms, and that is possible if I choose a time scale. So let me simultaneously give you the choices for my scales here, right? So if I choose a time scale given by L over UC, right, which is the time scale with which things change in the horizontal direction, in our case because there are variations in the gap width. So this is a sort of Lagrangian time scale associated with variations in the gap, and because the variations are slow, a long wavelength, we expect this time scale to be a short time scale, a long time scale. The short time scale would be H by UC. Anyway, so proceeding with this time scale, we would immediately see that if I replace this, I'll get UC square by L, but then if I again multiply and divide by H, I could take out UC square by H common and leave an epsilon behind. So I could replace this entire term by UC square by H epsilon after using the corresponding time scale and multiplying and dividing by H. Alright, so I actually have an epsilon UC square by H common in all these terms, leaving behind their scale components. So let's keep that in mind. Let's now move on to the other terms. Here I have a characteristic pressure scale yet to be determined, again divided by L, but I can multiply divide by H to get H times epsilon. Now in these terms I have commonly I can take out UC, again commonly I can take out H square provided I throw in an epsilon square to take care of the L square factor coming from here. And then I have G star. Okay, so I have now introduced all the scale factors, but I have yet to finish my order 1 scaling. So that requires for me to first identify the dominant physical force in the problem. And in this case, it's certainly going to be viscous stresses because of the thin gap nature of the problem, where I said that inertial forces are negligible. And so the dominant forces are going to be viscous stresses. So certainly to retain these viscous stress terms, basically the strongest viscous stress term here is dou square U by dou Y square, the transverse stresses, right, which makes sense for a thin gap. I then divide throughout by mu uc upon h squared. Right, so that would allow me to define immediately a g, which is basically the actual g star times h squared by mu uc. So here you see I can, if I want to choose u characteristic from the applied pressure gradient, I can do so by choosing uc to be g star h squared by mu, in which case g will just be 1. Or I would then get g to be some number if I had chosen uc to come from, let's say, the motion of the wall. So if I divide throughout by that, this g star will transform into g. At the same time, I'll have another component here in front of the pressure gradient, right? So this component also should be 1, because in general we expect the pressure gradients to arise in response to the variations in the viscous stresses as we move along the channel. Right, so I can choose my PC such that the pressure gradients balance are driven, let's say, by the viscous stresses rather than inertial terms, which is of course a consequence again of my thin gap behavior. So what I say is PC epsilon by h must be equal to mu uc by h squared, which means that PC is simply mu times uc upon h into epsilon, which means it's order 1 by epsilon. So this is one of the key, let's say, key basis or key outcomes of the long wave analysis, that the pressure, the characteristic magnitude of the pressure that develops in the thin gap region is large. It's order 1 by epsilon. Right, so what this means really, the outcome of the scaling, and basically what the scaling analysis implies itself, is that to drive flow through a thin gap, you do need to develop high pressure gradients. Right, so the pressures that are produced as a consequence of this thin flow are going to be large, and the thinner the gap, the larger is the pressure that is induced. So when I say pressure induced, it's easier to understand that in the case of a Couette problem. So again, going back to our schematic, imagine there is no applied pressure gradient. Rather, I simply move the bottom plate horizontally close to this wavy-wall. Now what happens is, if the wall were flat, right, you would have, if both walls were flat and you have the bottom wall moving horizontally, you would have a pure Couette flow where there will be no pressure gradients at all. So the pressure is whatever the pressure is, let's say in the outer region or at the ends of the domain, and the pressure gradient is 0. But the moment you have long wave variations introduced in the problem, there will be pressure gradients arising in the flow to drive the vertical velocities and to maintain conservation of mass. And those pressure gradients are going to be larger the thinner the gap is, right? Because to essentially what you're doing when you have a wavy surface is that you have to accelerate fluid to make it flow through the narrower regions, right, and decelerate it as it goes into the thicker regions. And the pressure gradients required to do that increase the thinner the gap, because the pressure gradients have to accelerate the fluid and overcome the strong viscous stresses present in such a thin gap. And so that is the kind of physical aspect that's captured by the scaling, which says that the pressures inside this thin layer, right, which is not the applied pressure gradient, it's the resulting pressures associated with the variations of the gap thickness. Right, that pressure is order 1 by epsilon. Of course, if there were no variations in gap thickness, the pressure gradient would just be G star, either 0 or some its applied overall value, and you would have basically PC would not exist. But even those those long wave variations are enough to drive very large pressures inside the lubrication layer. In fact, this is the pressure that supports mechanical devices which are in close contact or close to being in contact, such as in the journal bearing problem. The large pressures inside this gap is what prevent this inner cylinder from contacting the outer cylinder. And we will see this in action in applications of our theory later on in the lecture. Okay, so this is the key pressure scaling, the lubrication pressure scaling. So I can just write that down there. This is the lubrication scaling for pressure, which is common to all such thin gap problems, right? And it's a large, what it tells us is the pressure values are going to be quite large. In fact, order 1 by epsilon, whereas the viscous stresses themselves have magnitudes of order 1. So another important point here is that because of this behavior, if you calculate the total force on objects associated with the lubrication flow, for example, let's say the force on the wavy wall, right, which in the neighborhood of the moving flat wall, the force on the wavy wall is going to be dominated by the pressure, right? Even though the viscous stresses are strong, they are only order 1. The pressure, because it's getting applied over large distances, capital L, has to be of magnitude 1 by epsilon, so that dou P by dou L is the same order as the viscous stresses, right? The transverse viscous stresses. Alright, so all of that I've just said in words is actually inherent in the scaling operations that we have done, but it always helps to go back and forth and try to understand what the math and what the procedure is telling us, to build confidence and also to gain insight. Okay, so with this pressure scale now, we are now in a position to write down the scaled version of our equations, right? So remember, I multiplied throughout by this factor, mu uc by h squared, so this will just be 1 here. G star will get replaced by G. This term will again go to 1 because of my choice of my identification rather of the characteristic pressure. And then this term has to get taken over and multiplied by this factor to give me what you will see here is just a Reynolds number, right? So if I multiply throughout, I had rho uc square by h, right? Let's keep the epsilon aside for the moment. Which gets multiplied by h square upon mu uc. Right, so we get in fact rho uc h by mu, which is nothing but the Reynolds number. Right, so therefore my scaled momentum equation is going to be the following. I'm going to have epsilon times the Reynolds number minus dou P by dou X, now fully scale, plus G, its scaled version, plus dou square U by dou Y square, plus epsilon square dou square U by dou X square. Okay, great. So this is my U momentum equation. Now I can move on to write my V momentum equation. So that is going to follow the same scaling as before, except that where I have U, I'm going to have V. But because V characteristic is epsilon U characteristic, it's going to throw out an additional epsilon factor. So I'm going to have epsilon square times Reynolds number dou V by dou X plus V dou V by dou Y. Right, now the pressure gradient in Y, importantly, instead of having a division over, instead of having the large length in the denominator, I'll have the small length h. So to compensate for that, if I have to have the same pressure characteristic scale, what I will get is a factor 1 by epsilon here. Right, we had seen this before in earlier problems as well. I don't have any pressure gradients in the y direction, applied pressure gradients, so I have no g contribution. If you do have a vertical component, if you're doing gravity, then you will have a gy here. So, but it's just a constant, and you can always absorb that into the pressure. In other words, the pressure could be used to represent deviations not only from the applied pressure gradient but also from hydrostatic behavior. In which case, you could just renormalize the equations. In terms of a new pressure variable, and the problem would be the same. So we lose nothing by ignoring the effect of gravity. Effect of the vertical component of gravity at all. So we just won't consider it for simplicity. And then I have, of course, dou square V by dou Y square, but this time's an epsilon because instead of U we have V, plus epsilon cube now dou square V by dou X squared. right? And then let me just rewrite down my continuity equation, which is dou u by dou x plus dou v by dou y equals 0. So these are my scaled equations. Let me call them 1. Great. So right now, these are they are still the full two-dimensional Navies-Stokes and continuity equations, but I have scaled them accounting for the fact that I have a disparity in the horizontal and vertical or transverse length scales, and that's represented by the factor epsilon. So now it seems natural, seeing that we have the small parameter epsilon in various terms of our equations, to look to get a perturbation solution in this thin gap region, which could either be the full domain, in which case remember we are doing a regular perturbation in epsilon, or if it's only a part of the domain, then we're really looking for a solution in that thin gap inner region, and it's going to be a singular perturbation problem. In either case, we can now look for a perturbation expansion in epsilon. So let me just focus on the u variable, but this applies to all other variables. And so on. And now in this case, it turns out that the lubrication theory, which gives us, or the thin gap or long wave approximation that gives us useful results, arises at the leading order itself. So we can get immediately useful results just by considering this first term u naught and by neglecting all higher powers of epsilon. So we're only going to look at order of 1, right? And we are also going to drop the subscript naught for simplicity, right? Which also equivalents to saying setting epsilon to 0 in equations 1, because that's what gives us the order 1 term. Right, so we can use it as we can view this either as, after scaling the equations, I simply drop out all terms smaller than the order 1, that is, I just set epsilon to 0 everywhere, or I can view it as the leading order term, the order 1 term in a perturbation expansion. The second is nicer because it fits in to our earlier understanding of perturbation theory, and it also keeps the door open for getting successively better approximations to a lubrication theory if the need arises. Alright, so if we do this, the continuity equation remains unchanged. Let's now come to the u momentum equation. Here we see that we will lose the viscous stresses in the longitudinal direction, which makes sense because the variations in the x direction are so weak that the viscous stresses are epsilon squared times smaller than the transverse viscous stresses. So we retain the transverse viscous stress, the driving pressure gradient if it exists, the pressure gradients, disturbed pressure gradients that arise because of the waviness of the wall. And then when we look at the other side with the inertial terms, we see that it's epsilon times Reynolds. So these terms can be dropped provided Reynolds is at most of order 1. In other words, we're looking at problems where the Reynolds is relatively small. If the Reynolds number is large, then regardless of how small epsilon is, these inertial terms may be important, in which case we cannot proceed, with the lubrication theory will not be valid anymore. So therefore, in addition to epsilon being small, an additional requirement is that the Reynolds number is at most order 1. So let's write it down here. So we set epsilon to 0 with Re being less than approximately order 1. Right, so the Re has to be smaller than 1, or this is another way of saying it is that Re goes as small o of 1 instead of big O. So big O represents the exact magnitude of a term. Small o just means that the terms have magnitudes, you don't know what the exact order is, but it's going to be less than this order 1. So it could be order epsilon, epsilon half, either way. Alright, so with that idea then we can drop off the inertial terms as well, noting that the Reynolds number is not going to be large, so we cannot compensate for the small epsilon. So we drop off all these terms and the u momentum equation just reduces to right, you just have dou square u by dou I squares minus g plus dou p by dou x. And so you see now this momentum equation is nothing but the equation we would have written down for unidirectional flow between flat plates. So this is where the idea of treating the long wave variations, treating the problem as if it is locally a unidirectional fully developed problem, even though in reality it is not. But because the variations in the gap are long wave, and an approximation can be made in the following way. So it really does look like the flow is locally unidirectional from this equation. The difference being, of course, that v is not truly 0, which is why we still have this term in the continuity equation. Let us now look at finally the v momentum equation. Right, so that's this equation here. So you see, to take the limit, we can multiply epsilon throughout, and then if we set epsilon to 0, all terms are lost, and all we have is dou p by dou y equals 0. Right, so what this implies very nicely is that p is only a function of x and not a function of y. So these equations, right, are the lubrication or thin gap or long wave equations. Okay, now one point to mention here is, if we had a vertical gravity acting or some component of gravity acting in the y momentum equation, you would have had a constant here, but you can integrate through and write p as basically the constant into y plus, you can write dou p by dou y as the component of gravity times y and a constant. So the hydrostatic part you can then take into the pressure, and all you will have is the leftover variation, which you could say is the pressure variation along the bottom plate, for example. And then you could replace that here, and so the pressure gradients in the x direction would just be due to variations along the bottom plate. The variations in y would just be hydrostatic. So like I said, even if you had a constant here, it wouldn't change the problem. So for simplicity, we just neglect that effect, as it makes no difference, and we just have 0 here. So in either case, it wouldn't change the fact that these pressure gradients, dp dx, whether they are the true gradients of pressure anywhere in the thin gap, or whether they are the gradients of pressure only at the bottom wall, let's say, this term would nevertheless be independent of y and be only a function of x. Okay, so now the fact that this pressure gradient is only a function of x allows us, you will see, to directly solve this problem. Oops, I made quite a big typo here. This should be dou square u by dou y square, of course. That is the leading term. The dou square u by dou x square term is lost. Right, so the right hand side here is entirely independent of y, which means that I can immediately solve the equation for u by doing two integrations. So let's do that now. Let's call these equations 2, right, a, b, 2a and 2b, with the understanding that the right hand side of b is independent of y. So I can now solve b for u, but of course it's still in terms of the unknown pressure gradient dp dx, the unknown induced pressure variations. Alright, so what do I get from here? It's just a simple direct integration at this point. Right, so a direct integration would leave me with u equals minus g plus, in fact I can now write it as dp dx, right, because it's only varying in the x direction, times, I would have y square by 2 plus some constant times y plus p. right? And now I can determine the unknown constants using the boundary conditions, right? That u at the bottom wall is basically equal to capital U, as I said, and u at the top wall h of x comma t. So I replace y equal to h of x comma t in the above equation, and the left hand side u must be equal to 0. Right, this is the nature of the problem that I considered at the beginning, where we are moving with the top wall so that it's in the moving frame it has 0 horizontal velocity, and only the bottom wall has a velocity u, which is actually the relative velocity between these two plates or two walls. Of course, you could have had velocities on both walls, and the calculus would give you, you could do the calculus and get more general results, but we'll just stick with this for now. Alright, so if I make these substitutions, it's rather trivial to do this, and it may be a good idea for you to pause and then try to derive it for yourself. And so you should be able to show that from here the expression for u is just g minus dp dx, where g, remember, is the imposed driving pressure gradient if there is one. Yes, there you have it. So this is now the equation that we can obtain that tells us u in terms of the pressure gradients, the pressure gradients that arise from the wall variations, and in terms of the motion of the bottom wall. And you see that you have two components. This is a sort of local Couette component, and this is a local Poiseuille component. Right, so by looking at these two components now, you can see that they actually have exactly the form of the solution if you had a combined Couette-Poiseuille flow between flat plates. The difference, of course, is that h now is not a constant but is a function of space, and that throughout the domain y goes from 0 to h, where h is a function of space and time. So in some sense it's the same solution, the same solution expression for flow between flat plates, but which is now being modulated as the thickness of those, as the distance between the two plates varies along the channel. That solution is modulated. But then you could have written this down, I suppose, as a kind of heuristic approximation by saying I take the solution between flat plates and apply it locally at every point of this varying thin gap. But by doing it this way, you can see how it comes forth systematically as the leading order approximation in a perturbation solution of the full Navies-Stokes equation.